Good morning, everyone, and welcome to the Fiber Broadband Association's Fiber for Breakfast. We're now in our 38th episode of 2023. But before we kick off, I'd like to thank Wesco, the platinum sponsor of Fiber for Breakfast, and Qubitekk, our quantum series sponsor of Fiber for Breakfast. Today in DC, the Fiber Broadband Association and NTCA released our Playbook 3.0, Cybersecurity and Supply Chain Risk Management under the BEAD program module. This module can be found on our website. So basically in the Notice of Funding Opportunity, as we like to call NOFO, released by NTIA, it requires eligible entities to ensure that prospective grantees of the BEAD funding attest that they meet certain cybersecurity and supply chain risk management requirements. These requirements can often be combined into a single cybersecurity and supply chain risk management plan. So the module we released today summarizes the NOFO's cybersecurity and supply chain risk management baseline requirements to which the prospective subgrantees must attest, and then provide recommendations on how eligible entities can work with subgrantees to meet these requirements. So everything you want to know is in this module, so look it up. Back in August, NTIA issued a proposed BEAD Build America, Buy America waiver for comments. If you're at our conference, you saw NTIA there talking about this. So those comments are due to NTIA tomorrow, September 21 at close of business, and the Fiber Broadband Association will be submitting comments, and we encourage all those that are interested to submit their own comments. And on the Hill today, the House Energy and Commerce Subcommittee and Technology Committee, actually tomorrow, will be holding a subcommittee hearing entitled Connecting Every American, the Future of Rural Broadband Funding. This hearing is going to examine the effectiveness of the federal over 130 broadband funding programs to aid in bringing and expanding broadband connectivity to the unserved and underserved, and consider how everything should operate in the future. Also today on the Hill, Senator Barroso from Wyoming and Sinema from Arizona will be introducing that Close the Gap Act, which is a very important bill to streamline the permitting process. Our next final and Regional Fiber Connect workshop for 2023 will be in Minneapolis on October 24th. So registration for this event has been really strong, so you don't want to miss it, so please register today. So I'm really excited that today on Fiber for Breakfast, we're kicking off our quantum series with our quantum sponsor, Qubitekk. So during the next 6 months, we'll be exploring quantum networking topics once a month on Fiber for Breakfast. As fiber enables our quantum future, we want to keep you informed. So that brings us today's Fiber for Breakfast session with Dr. Duncan Earl, the co-founder, president, and CTO of Qubitekk. We'll be discussing quantum technology, what it is, and why it will soon matter. Before I formally introduce today's guests, I'd like to introduce Trish Ehlers from our team, who's going to walk us through some housekeeping items.
Thanks, Gary, and good morning to everyone who's joined us this morning. Before I go over a few logistical items, I'd like to once again thank the platinum sponsor of Fiber for Breakfast, Wesco, and the quantum sponsor of today's webinar, Qubitekk. Now, if you'd all keep in mind that everyone's in listen mode only, to ask a question, you can type it into the question box located within your control panel on the right side of your desktop screen. We'll host a Q&A session with our panelists at the end of today's webinar. This presentation is being recorded and will be available on FBA's website within 24 hours. You can find the recording in the Events tab under the Fiber for Breakfast drop-down option. At the conclusion of the presentation, you'll be prompted to complete a brief feedback survey. If you could take a minute to do that, we really appreciate your input. I'll pass it back to Gary now to introduce our panelists and get us started. Gary?
Well, thanks, Trish, and good morning. I'm Gary Bolton, the president and CEO of the Fiber Broadband Association. Last week on Fiber for Breakfast, we had the pleasure of hearing from our good friend Jeff Hainan from Del Oro, who discussed setting the record straight on PON equipment trends. And Jeff had two key takeaways. First, he anticipates that we'll see the inventory drawdown complete in the second half of this year, and he anticipates strong growth in the PON equipment market in 2024 and 2025. The other key takeaway is that the cable industry is moving to fiber to the home in a big way. Today on Fiber for Breakfast, our guest is Dr. Duncan Earl. the co-founder and president and CTO of Qubitekk, who's going to be discussing quantum technology, what it is, and why it will soon matter. Dr. Duncan Earl is the co-founder, president, and chief technology officer at quantum networking company Qubitekk. Dr. Earl, a physicist, spent nearly 20 years conducting energy and defense-related research and development in Oak Ridge National Laboratories in the fields of quantum sources, quantum computing, and quantum cryptography. Today, Earl's focus lies squarely in applying his findings towards building quantum networks and critical to becoming the quantum-enabled internet. A nationally recognized pioneer in the field of practical quantum applications, Dr. Earl holds numerous patents and has served on steering committees for organizations including QED-C and NIST, and frequently advises policymakers about quantum networking solutions to some of the country's foremost challenges. So welcome, Duncan, and for our audience, please type in your questions as they go, and we'll work them into the Q&A at the end. With that, let's get things kicked off.
Thanks, Gary. Appreciate the introduction and really appreciate the opportunity to speak to the group today. So yes, the title of this presentation is Quantum Technology, What It Is and Why It Will Soon Matter, emphasis on soon. If we advance to the next slide, maybe a great way to start this is just talk a little bit about the buzz around quantum. You may have already heard some about quantum technology and how it's going to disrupt and revolutionize businesses. In fact, even at the Fiber Connect conference last month, we had a session and a number of talks that were really focused on this technology and how it's going to affect fiber broadband providers. So it's something that's gaining steam. Definitely over the next year or two, it's going to become more and more of a mainstream topic. So we hope you're going to hear about it here first, and then it'll make put some context to what you'll hear in the popular media in the coming years. So a great place to start is just to talk a little bit about quantum physics and what that is exactly. In short, quantum physics is the physics of the very small. When you get down to tiny particles like photons, which are particles of light, they behave in a very different way. I think all of us are familiar with the world that we live in. When you drop a ball, gravity sucks it to the ground, and the earth stops it. And we're familiar with basic concepts of space and time and how you move through these elements. But when you start looking, and they call that kind of classical physics, all of what we're familiar with at the macro scale, you can just call that classical physics, which is very well understood today. But when you start pressing down into the smaller and smaller world, getting down into these individual particles, the subatomic level, the physics becomes very, very different. These subatomic particles behave and exist in a world that is not something we're going to be very used to. And so in this presentation, I'm going to talk about two specific behaviors of these subatomic particles, because those behaviors specifically are being applied today and are in some of this quantum technology that we're going to be looking at. But I guess I would like to request that everyone sort of suspend your intuition of physics. we know the classical world, but we're going to be talking about a very different world where things behave very differently. So that's sometimes hard to do, but if you could please maybe suspend for at least a little bit what you know about space and time, and we'll take a little different view at those elements. Okay, if we could go to the next slide, the very first physical property that I'd like to touch on is something called entanglement. So when you get down to these small particles, and sometimes I'm going to talk about light and photons, because oftentimes they're the very easiest to work with. And we also send them over fibers, and most people have some familiarity with photons. But we can create these particles that are entangled. And entanglement, what that means is that you could have two particles that could be unique entities. They could each be distinct particles, and they could be separated by a very far distance. So they could occupy a unique point in space, and they could be very, very far away. But when you do something to one of those particles, the other particle is going to feel it, or it's going to react to that. And so it's going to do that instantaneously. It's not going to require any communications between these two particles. It's almost like these two particles are the same particle, but they're just in two different places in space. And so you can probably pretty quickly start imagining some applications for that. If you have two particles that you can separate in space, but they can, quote unquote, kind of feel each other or respond to each other, but there's no communications between them. There's nothing to intercept between these two photons as they have a relationship with one another. That can be a very useful property, specifically for communication security. So entanglement, we understood it about 100 years ago, but we've only gotten to the point where we can control it and create these systems, over the last few decades. And so entanglement is a feature of the quantum world that we can exploit for information security, for teleportation, for other sort of really cool applications, which we'll talk about later. But it's one of those fundamental principles of the quantum world. So entanglement is the first, and if we advance to the second slide, or the next slide, superposition is the second one I really want to share. So we're not going to dive too deep down this rabbit hole of quantum physics, but I do want to touch on these two because they are relevant for the slides that will come later. So the second phenomenon is something called superposition, and the idea here is kind of the inverse. You can have one particle that normally would have a certain value in the classical world, but in the quantum world, it can have many values. So in the classical world, we might have a coin that you flip and it ends up being either heads or tails. In the quantum world, you could flip that coin and it could be heads and tails simultaneously, which is a really weird sort of a possibility. And another way I like to describe it, because it helps a little more to understand how it can help with computing, is you can imagine going down a road in the classical world and coming to a fork in the road where you could either go left or you could go right. And in the classical world, you have to choose. If you go left, you're going to encounter everything that left fork has to offer. If you go right, you're going to encounter everything that the right fork has to offer. And in the classical world, we make a choice and then that's done. It's done. It's kind of defined at that point once the choice is made. In the quantum world, when a particle like a photon gets to that crossroads, whether it goes left or it goes right, it doesn't have to really decide. In some respects, at that point in the quantum world, you can think of it almost as though there's two universes that exist. There's one where the particle went left and it encountered everything that was on the left side. And then there's a parallel universe where it went right and it encountered everything on the right side. And there actually could be 1,000 of these parallel worlds that are simultaneously occurring at the quantum level. So that's a very strange sort of behavior that we don't have in the classical world, but it ends up being very, very powerful. Superposition ultimately is the property that we're exploiting to do these super fast computations with quantum computers. And that's probably about as far as I'll go in terms of describing the physics. But I hope people take away from this presentation that entanglement and superposition underpin a lot of these new technologies that are emerging. So if we go to the next slide, how does this compare to the classical world and the classical information that we're traditionally working with over optical fibers? Well, in the classical world that we know, we think of information as being in bits, and those bits are usually binary values of either 0 or 1. For quantum systems, they're going to be communicating using quantum bits or qubits, and those qubits can be 0 and 1. They really can have sort of an infinite number of states that they're in, and that's going to give them a lot of power. On the classical side, our deterministic binary data, we have calculations where we put data into a system, the data is known, and then we get an output, and the output is known. With quantum systems, it's very different. You're putting in data that is semi-known, pseudo-known, and then you're getting out something that's probabilistic. So it's not like a calculator where 1 + 1 = 2. It's really a number plus a number equals another number, and probability determines what those outputs are. In addition, classical bits, we tend to process those sequentially. the hardware assumes that you have one function, then another function, then another function, and we sequentially work through a problem. With qubits, we're simultaneously working through a problem. Again, we're leveraging those parallel universes or those parallel worlds to work a problem simultaneously. And again, this is not parallel hardware. The qubit is what's actually being parallelized. So the qubit naturally wants to push into these other states or these other worlds to do a computation. So everything in the classical world, of course, is based on the physics of the classical, and everything in a quantum computer is based on quantum physics. This is a very short sort of introduction to quantum physics, but as you can imagine, there's a lot of nuances, and this is a fairly deep rabbit hole you can go into to learn more about these new technologies. But these are the two phenomena that ultimately underpin these differences. Okay, and then if you go to the next slide, just to kind of drive home this point on the information side, is just a quick graph that when we think about 10 bits of information, we process those 10 bits sequentially, and then we have now some new information, but it's always pretty much 10 bits that are being moved from one level to the next. When you think about 10 quantum bits, again, those 10 quantum bits can get parallelized as much as you want or as much as the hardware will support. And so you can contain in 10 qubits significantly more information, exponentially more information based on how you define your quantum systems and what you do to those qubits. So if there's nothing else that you take away from sort of this quantum discussion, please know that 10 qubits can do way more than just 10 bits because of this inherent nature of these quantum bits to store and to really process information. Next slide, please. Okay, so what do you do with this type of technology? Where are we likely to see this technology first show up and have an impact on our lives? It's really kind of three places that people frequently talk about, and I'm going to go through these very quickly. But the first is on information security. So we know that cybersecurity is a big deal, especially with infrastructure. What we're going to be able to do with quantum networks, fiber optic networks that share entangled photons, is develop security that can't be intercepted, can't be cracked, much higher levels of security that we can distribute and use for things like infrastructure security associated with the electrical grid, oil pipelines, things like that. Next slide. The second area where we expect to see early utilization of this technology is in the speed up of certain systems. So just one example is drug discovery. Currently, it costs about $2 billion in about 10 years to develop a drug. A lot of that is because we can't model the basic chemistry involved in drug discovery. So being able to speed up what we can model, eventually significantly speed it up with quantum computers, should reduce the cost to develop drugs and get those medicines to people sooner, and hopefully save lives and cure diseases faster. And then the next slide is focused on sensing, where quantum sensors have the potential to be significantly more sensitive than the sensors we use today. Fiber optic networks that tie together these quantum sensors can potentially detect earthquakes 2 hours before they occur, due to using these fiber optic networks as very sensitive vibration sensors. So the potential for quantum technology to really impact our lives, potentially save our lives through networks like these, is an expected outcome. And then the next slide is on the market. Of course, the reason everybody's investing in this is hopefully to save lives and to impact our everyday life, but also it's to make money. And we know from studies like the McKinsey study that came out last year that this is over $100 billion market by 2040. That's just for the quantum pieces, the quantum components, and the companies. The people that actually use this quantum technology, it's expected to result in over $1 trillion of additional revenue for the users of this technology by 2040. And I'll just quickly hit this last slide. I won't go into in detail here, other than to say, as we move from bits to qubits, the fiber broadband providers are going to be critical to moving these qubits around over fibers. And so we've got a seminar here, or a series of seminars over the next several months or 6 months that really kind of introduce the community to this and talk more about the applications. So I hope you'll join Gary and the other presenters in this series as they dive deeper into these topics. And with that, I'll pause there and turn it back to Gary.
Well, Duncan, I'm fascinated by quantum technology and really excited about, what we're enabling with fiber networks. Can you start with maybe just, what type of calculations are best for classical computers and what are going to be best suited for quantum, and kind of help differentiate?
Yeah, that's a great question. And I guess I would say that, quantum technology isn't meant to replace classical technology. There's still things that classical technology does exceedingly well, and quantum isn't really meant to replace that. It's just meant to augment it. So whenever you have a lot of data that has to be processed and complex decisions that have to be made based on that data, that's where you're going to have the real strength of quantum technology. So optimization is typically one of those areas. Modeling of physical systems is another. And so as quantum computers start to stand up, they're going to augment these classical systems. It's not going to change the way your laptop looks or some of the Excel and Microsoft Word and things like that, but it'll be the engine that's going to be driving a lot of this number crunching around data mining and optimization and modeling.
So while fiber really enables quantum networking, the limitations, we have some distance limitations with quantum repeaters. Can you talk a little bit about that and where we are with kind of cracking that nut?
Yeah, with kind of the state of the technology today, most of the fiber networks are kind of metro level. They're smaller networks that are typically isolated. So you'll see a network that might be across a downtown region in a city, and then a few cities away or in another state there might be another network that also is just in the boundaries of a city. Right now we expect to see these networks stay small for probably the next 2-3 years. As we understand better how to tie them together and how to do long distance communications. So many isolated quantum networks is what we'll see over the coming years, and eventually we'll be tying all those together to really create more of a quantum internet. Right now we have more quantum local area networks today.
What about the repeaters? Can you talk a little bit about that?
So repeater technology is all based on the ability to create a quantum memory. So these qubits that I was describing, we need to be able to capture them and store them for a certain amount of time, and then to release them later. If we can build these quantum memories, we can build the quantum repeaters that will drive a lot of the long distance communications. Right now, there are a number of very mature technologies on the quantum memory side. So people are working towards these quantum repeaters. I believe over the next 12 months, you'll start to see commercial versions of quantum memories, and soon after that, commercial versions of quantum repeaters. So we're not far, but there still is some work to do.
So got tons of questions from audience. One is, so what kind of requirements will be needed for quantum technology?
Yeah, and specifically, like, what about fibers? I know that that's a question we get a lot. Pretty much all of the quantum network systems that are being stood up today are attempting to use traditional SMF-28E, telecom fiber. So the goal is not to need to rip out all of that fiber or come up with a new optical fiber, but rather to utilize what we already have in the ground. Having said that, the job gets a lot easier when it is dark fiber or fiber that can be dedicated to carrying these qubits so that they are preserved over the optical fiber. Everything that people are familiar with at equipment hubs in terms of transmitters and receivers, detection systems, we have the same thing on the quantum side. It's just that everything's more expensive and bigger on the quantum side. But you have transmitters, generators and transmitters of quantum bits, and you have devices that detect those qubits and measure their states. So there is an analogy to the classical systems. It's just the maturity isn't nearly at the level of classical communications, but similar categories.
So, I mean, you spoke about the role of fiber optics in quantum computing. So one of the questions is, our audience has said they've heard it's essential fiber is essential because quantum computing only works with photon movement. Is that right?
I would maybe add a little to it. So definitely fibers are needed to network together quantum technology, whether that is communication systems, computing systems, or sensing systems. You need a fiber optic network to tie all that together, and you need a fiber optic network that's meant for quantum bits. But the computing one is an interesting application, because as they build bigger and bigger quantum computers, and they really want to build, massive quantum computers, they know that they ultimately need to go to a distributed computing model. So you need to have 1,000 quantum computers on a fiber optic quantum network, all working together in order to scale up this technology. So the quantum network really becomes an integral part of building a large quantum computer. So that's kind of how the fibers fit into these scaled up quantum computers. They're what tie it all together.
That really scares me when you think about some of the proponents to say, oh, you don't need fiber, you can do things over satellite or over fixed wireless, and it really is going to leave people on the wrong side of the quantum divide.
Yeah.
So one of the you mentioned quantum memory, and that differs from traditional memory, so cache, DRAM, and so forth. Can you explain in what ways?
Yeah, and maybe just real quickly to pick up on your point there about the fiber component. I know there's a competition between fiber and wireless. This is a good application where we can't do it wirelessly. It's got to have fiber in the ground in order for these quantum systems to work. So just another advantage of putting fiber in the ground to customers. But yeah, I'm sorry, I lost the trail on your question. What was the?
Oh, it's just about, well, just to add on to that, unfortunately, Senator Cruz issued a report earlier this week trying, saying it'd be cheaper to do wireless or satellite, and I just hope the people of Texas value the fact that they want to be in the quantum future. So hopefully people won't make bad mistakes on critical infrastructure. But the question was on quantum memory, how it differs from traditional memory, in what ways?
Yeah. So definitely it's much more simplistic, or I guess I should say that a little differently. I think about the, back in the 60s and 70s, where early disk drives were big rotating drums that, they were trying to encode a few bits onto. That's kind of the where quantum memories are today. It's not that they're trying to store gigabits worth of qubits. They're really just trying to capture, hundreds to thousands of qubits within these traps. And typically these are trapped ions or neutral atoms that are suspended, that will intercept a photon, hold on to it for a while, and then those atoms will release the photon at some later time. So the amount of time that they're stored in memory really is only on the order of microseconds or milliseconds. So it's a very different kind of time scale and size scale for these memory systems. But with everything, that's where we're at today. 10 years from now, we'll be laughing at the capabilities that we have today. I'm sure that technology will advance very quickly.
So I know that Chattanooga has the world's first commercial quantum network. And I mean, I can't even fathom how amazing it is that average person will be able to have access to cloud-based quantum computers and things like. I mean, so what is the time frame? When does this go from like a science project to this will be? I mean, just like you look at ChatGPT, storm the world in a few short months. I mean, what does it look like here?
So we are there today with cloud-based quantum computing and with commercial quantum networks. You can now subscribe to these networks and these computers today. It's not definitely a household name, some of these systems, but we're moving quickly towards really the accessibility improving and others becoming involved. I would say we're probably about 2 years away from the ChatGPT moment for quantum. That's coming, but we're not there yet. But it is commercial. The networking side and the computing side is commercial today, and we're only going to see those grow in the coming months.
Well, I have to say you have one of the coolest jobs on the planet, and I'm rooting for your great success here, because I think just I live in Huntsville, and genome sequencing, we're one of the top genome sequencing places, and just the potential of quantum networks and quantum computing just is unfathomable. So thanks, Dr. Earl.
Appreciate that. Appreciate the opportunity to talk, and I hope everyone catches the other presentations in this series. They should be very good.
Yeah, I mean, that's the plan here, is that every month we'll take people next step further into the quantum world. So hopefully by the end of 6 months, we will all be experts in quantum technology. So thank you, Duncan. And
Thank
we're
you.
just really excited about the whole potential of quantum technology and appreciate your research and efforts to usher us into the quantum age. And I want to thank everybody for joining us today on Five for Breakfast. We're going to get back together next Wednesday with our good friend, Quinn Jordan, the Executive Director of Mississippi Broadband Association. He'll be discussing Connect and Literacy Fund that they put together. So you're not going to want to miss that. We'll see you guys next Wednesday.